All right, so now we're going to move on to Kepler's laws. And Kepler's first law of planetary motion says that all planets orbit the sun in elliptical orbits with the sun at one focus. And so if we were to draw this, what we want to draw would be, you know what, I'll just take an ellipse like this because I can use it on this tool. I know it's cheating still. So here's the ellipse. We'll put our little planet right here. And what we're saying is that the sun goes at one of the foci of the ellipse, and then you have the other focus, say, right here, like that. And then this is the path that the planet follows. That's all. Now, Kepler's second planetary law, it's supposed to say second law. I'm clearly ahead of the game here with my physics question writing ability. Kepler's second law of planetary motion says, and I'm actually going to copy some of this from above so I can draw it properly, and it would go, whoops, that's not what we want. Wanted to copy the ellipse. Take this, put it back here. There we go. So Kepler's second law says that planets sweep out equal areas in equal times. The idea is that if we have our little sun right here, and we have the planet orbiting, so if this here is, say, 1 month worth of motion, like this, meaning the planet moves from here to here, and this is, say, like 2 months worth of motion, then out here at the edge, we sweep out an area that's longer and narrower. This is also 2 months worth of motion, let's say. And what we're saying is these two areas are equal. And in order for them to be equal, we're moving faster here closer to the sun and slower here out at the edge. So that's kind of the area shaded in here and here. And then the next thing that we have is we're going to use Kepler's third law to answer the following questions. So we have Earth 93 million miles away with an orbital period of 365 days. So our first question says, if this is Neptune's orbital period, we want to know, it's 148 years, how far away is Neptune? And how many miles is that? So here's what Kepler's third law says. It says the year squared divided by the average distance cubed of planet 1 is T2 squared over R2 cubed for planet 2. So in this case, we have 1 year's, so Earth has 1 year to orbit the sun, and its distance is 1 AU away. Okay. And so Neptune's orbital period is 148 years, and its distance from the sun is R cubed. Now we can rearrange a little bit, so we're going to get 1 equals 148 squared over r cubed. And when we actually calculate 148 squared, just so you know, that's going to be 148. So that'll be 21,904. And I'm just going to write that in this next line here. So 1 equals 21,904 over r cubed. We'll multiply both sides by r cubed, so we'll get r cubed equals 21,904. And so when we take the cube root, r is going to end up equaling, let me get our answer, shouldn't be so hard to get, that will end up being 27.97 AU, or about 28 astronomical units. To figure out how many miles that is, we'll take this. So this is one version of the answer. We wanted it in AU. And then in miles, we'll take 28 times 93. And that'll give us 2.6 billion miles. All right. Similarly for Mars, we take the Earth data, 1 over 1, equals the period of Mars squared over this 1.5 cubed. So we're going to end up getting that T1 squared equals 1.5 cubed when we do the algebra. Sorry, this is just messy. So 1 squared divided by 1 cubed equals T2 squared over 1.5 cubed. When we isolate T squared, we get that it's equal to 1.5 cubed. And when we actually isolate T by taking the square root of both sides, we're going to get that T2 is about 1.83 years. And when we take 1.83 and times it by 365.25 days, we're going to end up getting about 671 days. Awesome. So that is where F period ends their practice test. And then G period, you have an additional set of calculations to do related to the gravitational force of attraction between two objects, which we're going to talk a little bit about next week. And also, we're going to actually derive where Kepler's law comes from in the next page.